All right, so we're back, I believe, and I'm going to refresh the chat. We should be good to go here. Hello, hello, hello. Good day, everyone. Let's get to the next question. Minimum size subarray sum. So today was kind of slow. I only got 2 problems done. I feel like I probably could do more and should do more, but for now 2 problems will be sufficient. Given an array of n positive integers and a positive integer s, find the minimal length of a contiguous subarray of which the sum is greater than or equal to s. If there isn't one, return 0 instead. Given an array of n positive integers and a positive integer s, find the minimal length of a contiguous subarray of which the sum is greater than or equal to s. If there isn't one, return 0 instead. This is kind of a play on the maximum subarray sum question, where the maximum subarray sum is sort of a classic problem, and the idea is to find, of all of the contiguous subarrays that you can, when you add them together, to find the maximum sum of all those subarrays. The maximum subarray sum, and it's an interesting question. It's got a pretty nifty solution as well. However, this is a slight variation on that, where you're looking for the smallest contiguous subarray in terms of size, and you're looking for, of all of the contiguous subarrays, that the sum exceeds a certain value that they give you as a parameter. So what's interesting, so this question could be done at least in quadratic time, because you can filter on every, because there's a quadratic number of contiguous subarrays, and you can filter on the quadratic number of subarrays, and then you can actually filter on this condition, the sum is greater than or equal to s, and then you can actually then find the minimal length of those possibilities, the one that has the smallest length. So there's 2 conditions here. One is minimal length of contiguous subarrays, and that's of the sum of the subarrays that have the sum greater than or equal to s. So it seems to me that there are some possibilities. I'm thinking about, how can you do this in linear time? Can you do it in n log n time? It seems like the first thing you want to do is find the subarrays that have a sum greater than or equal to s. That could include, if you figured out the O of n solution, try coding another one, which is O of n log n. Oh, that's interesting. Oh, so there is an O of n and an O of n log n. Well, normally they don't tell you that. You have to kind of figure that out for yourself. But let's try to find the linear one, and then we can think about what the n log n one might be. No, don't want that. I don't know what it might be. I have to think about it a bit. Want the minimal length. Huh. Okay. I want to say you could use a sliding window for this one, where you have a sort of pointer pointing to index A and pointer pointing to index B, and they start off at 0 and 1, right? A and B, or you just have A at index 0 and B at index 1, and when you increment, so if actually you could start at A at 0 and B at 0 at the same point, right? So that could be your initial subarray, and then you say, okay, if you're not larger than the sum, then increment to the next subarray size, or to increment to B, and then if you are larger, then shift A over until you're not larger again. And so the idea here is, yeah, so why this actually should work. And then right, then when you shift A, if you're then under the sum, then you would shift B over. If you're over the sum, then you would shift A and B over to the next position altogether. Right, and between each, yeah, so you'll that'll be linear time, and then you can take of each of those solutions, you just check against your the length. Every time you go over, check against the length. And obviously, if it's the first time, then you save that solution, and then after every point afterwards, every time you see something that's larger, you check it against what you've already saved. So that's a sufficient and that's linear time, and I think that's correct. And the proof for correctness is what you're going to do is you're going to say take every subarray sum or every contiguous subarray that's positioned at the ith index, so A at point A, right? And that means that if you consider all of the subarrays that start at some position I, the only option you have is to move to the right for B. So you have A is fixed, and you would move B. Once you've already exceeded S, there's in order to get the minimal length, moving past that point is just unnecessary. So actually, you can then consider the next fixed A. So you could start at the A at index 0, move to the right to find the sort of minimal length of a contiguous subarray that's greater than or equal to that sum, and then move to the next position. And if you don't find any that ever exceed S, next fixed A, so move to index 1, and then check all from B from 1 to the end. Now, what's interesting also is obviously the interesting part here is that you don't need to start from A every single time, because you know that when you remove one of these elements, you should, what do you call that? You should. So actually, here's something interesting. Once you move, no, this might not be linear then. Actually, when you remove an element from A, if you're still greater than the sum S, it's possible that you could remove elements from the right side, from B. You can move B back to A. No, it's not possible, right? Because previously you had to add an element in order to get over S. If you remove that element, you will necessarily be under S. So you'll never move B back, because now you've moved A to the right. If you go under, or if you're still over, then you can go to the next value, right? You'll never move B back, because B necessarily would have to cause you to go under, because you've now removed. So you never move B back, right? Yes. Yeah, that's it. That's the algorithm. It's pretty straightforward. So let's try it. Let's give it a shot. So we're gonna say int. What do we want to? Ret. It'll be 0, and then we're gonna say for int A equals 0, and B equals 0, and then we just want to say no, you don't even want to do that. You really could just do A. You really could just could do it like this, A, and then it's really going to be like A, something like this. So A, A is less than or equal to it's actually kind of I don't know. I'm not sure how we want to do this. It's going to be an interesting loop. A is less than or equal to nums dot size, or just less than nums dot size, and B is less than nums dot size. And the way that this is going to work, I don't know if I should just do a while loop for this, because this is kind of funky. This is kind of funky. This whole thing. I don't know. I can maybe rewrite the loop once I'm done. So we'll just do a while loop while true for now, and we'll modify it later. So there's another loop here, which is going to be while, and we'll have a running sum. I don't know, we'll just call total. Initially 0. Total should be, so let's say sanity check. If nums.empty turn 0. So we always have at least one value in there. We're going to say nums of 0 initially. Now we're going to say while total is less than s, we're going to increment b plus b, and then total plus equals nums of b, right? And then at some point you'll be over, and then what you're going to do is ret equals standard, the lesser of the two, minimal length, right? Okay. So start at nums.size. Excuse me. Of ret and b minus a plus 1. And then you're going to say, then you're going to increment a and total minus equals, or actually minus equals a, nums of a, and increment a. So increment b, increment the total, and you want to say end b is less than nums.size. Right, so if b, actually, I think I'm doing this wrong. There's probably a better way to do this. Just coding it up kind of in a funky way. If I don't know, we'll hold on for a minute. I'll think about it in a second. I'll come back to it. But yeah, b's got to be less than num size minus 1 in order to increment. Otherwise, you won't even bother incrementing again. You increment a here. The problem with this is there's a few issues here. You still need to break from this loop, and then when do you break? And this actually has to update correctly too. So start off with the total, the first index. then you would add the next index, total is less than s. If the total is greater than or equal to s, then you take this minimum, it would be a 1, and you would move a, and you would say, you know, if you would say if a equals b, then you would increment b too, right? Both of them have to go. Increment them both. If they're on the they're on the same spot, you gotta increment both of them. Then let's say you have to increment b a few times here, right, to increment the total. So you scroll it over a bit, and then you scroll a. Let's say, yeah, now the total is greater than or equal to s. Scroll a, and now the thing is here. If you get down here, and the total is this is kind of tricky. I think you would exit the loop, right? There's a certain point where you exit the loop. I'm not sure exactly where or when. I want to say, like, if total is greater than or equal to s, then we do these things. Right, because this could break, B could just go right off the side, basically go right off the side on the right side. And then A, you're still not greater than or equal to S. Right, that's the condition I'm trying to handle. And if you're still not greater than or equal to S, then you don't want to update. You don't want to modify the total either. And I mean, you would do this no matter what, I think. But at that point, if this is the case, there's no reason to update. There's no reason to even loop anymore, because if you move A further down, you're just done, I think. So yeah. So what you want to do is actually, hold on. What you want to do is really you would say, if total is less than S and B is greater than or equal to nums that size -1, or yeah, and then you actually want to break. You're just done at that point, right? Because moving A over more at that point is not going to matter. Now, does this get the last case when B is all the way at the end? Let's say A is just one element to the left, B is all the way at the end, total is greater than or equal to S. You would update two elements, subtract one, they're not equal to each other, increment A. And then here you wouldn't even bother looking at this. It's still greater than or equal to S. You would update, subtract A again. A and B are equal, A and B are both now outside. And then you would say this is false. And then this should be less than S because it should be 0. Unless S is 0. So then the total goes to 0, and both of these are outside. And then you actually get you have a problem if you do that. You just need to do A is less than or equal to less than that size, and B is less than nums that size. Okay. Yeah, this will push you. That'll push you out. That'll prevent you from executing this code when A is outside the bounds. Now there's one more issue here, is that if this is edge case here, we'll handle this edge case separately. Yeah. If, excuse me, there's a way to like accumulate, what is it called? It's like, there's a way to just sum all the nums. Accumulate CPU ref. I think that's what I want. First, last, 0. Yeah. So we'll just say, or just call it X. Actually, you don't even need to. It doesn't matter. You can just do standard accumulate. Nums.begin, nums.end, 0, and if that's less than S, let's return 0. And then we don't have to worry about it here. Does this work? What does this do? Oh, look at that. Okay, get some test cases in here. This seems like it took me a while though to do this. I don't think particularly liked this approach here. There's like a bunch of a bunch of different cases I want to test. I don't know, man. This is interesting. Invalid test case. Signed integer overflow. Okay. Line 9, character 11, 21. It's an invalid test case though, right? Which one is it though? So let's do this. Yeah, that was kind of what I was wondering. It wasn't clear which were the test cases that were valid or not valid. Okay, looks like S needs to be positive, and S is a positive integer, so I don't think it can be 0 either. Okay, it works in those cases. That's great. What is up with this one? Also, okay. So it can't be, right, can't be, it has to be positive integer, so it can't be 0. Can't be -1 either. Alright, can't be -1, can't be 0. How about it's empty, the array? Okay. Alright, and I don't know, I guess we'll do some random test cases then. See how well that goes. How well of that goes. Runtime error. Oh, nice. So it looks like there's a parsing error of some kind. Yeah, that's a parsing error. Too many commas in there. All right, looks pretty good. So there's got to be a better way to write this code, though. This is so funky. You know how I wrote this? Let's go for it. Nice, got it. Sweet. Yeah, this is really awkward how I did this. I want to say something like, we're going to increment a at every point, right? See, this could just be a for loop. For loop, and you can put plus plus a. I mean, I was going to do that, right? That definitely could have been done. And actually, you can do int a equals 0 because, right? Definitely. Now, b is going to be, you could say, well, for b could start off at a. No, so b is actually got to persist between iterations. So actually, no, you don't want that. You're going to increment b at each step here, but I think it's better to use the while loop here. And then thinking if there's a better way to do this. Increment b, increment the total. I don't need that anymore. Definitely this can be cleaned up here, but I'm wondering if there's a way to clean this up too. I kind of prefer it this way. This is kind of straightforward. I don't know. Maybe there's a better way to do this. I kind of prefer it this way. There might be a better way that I just don't realize. In terms of the logic, I think, yeah. I want to say that this is going to break anyway. You don't need to terminate early. You really can just say if total is greater than or equal to s, or b is, you can just do this. That's really all you got to do. I mean, I think this works fine just the same. It's a little slower because you don't terminate early anymore, but you really don't have to terminate early. I'm thinking like if there's a better way to, because like if I had to code this up again, I would kind of fumble my way through it. This is how I did this, how I did it this time around, which is kind of gross, kind of ugly, kind of slow. I think that's kind of just the only way I know how to do it. How else would I do this? I don't know. I'd have to really think about it for a while, figure out, okay, what parts of the code can I kind of remove? It's a little bit like, I don't know, there's kind of like, I guess there's a little bit extra going on here. So, yeah, while the total is less than S, you want to keep incrementing B and adding B to the total. And then if you are greater than the total, then you want to go ahead and update. And then you're going to shift A and just check if A is equal to B. You want to shift B also. And then eventually you're going to hit a point where A is always going to be, your total is always going to be smaller. Actually, I kind of prefer the other way. I did actually like that better, to terminate early. This is a little bit more efficient. Oh. What happened? Yes, it's like slightly more efficient. I mean, not really. Whatever, it doesn't really matter. I'm trying to figure out how I can write this more concisely, like with less, I guess just less stuff going on here, less code. But I don't think I can. I think this is it. Or there is probably a way to do it, but it's evading me at the moment. Well, anyway, that's my solution to this problem. That's the O of n solution. The n log n solution, I guess you'd have to do some kind of divide and conquer kind of a deal. I really wouldn't know that offhand, what to do. I'm thinking if I could just describe it, the n log n solution. Gosh, no kidding. What you can do, what you could do is you can do a summation. It's so there is an n log n solution that you can do. It's pretty funky, but it can be done. What you're going to do is at every index, you're going to find the corresponding, A index right on the left side. You're going to find the corresponding B index on the right side. That's the smallest value, such that the sum up to that point is minimal, the smallest length. So the value closest, that's also still greater than or equal. And so you can do a binary search over the indices. And what you're going to want to look to do is first you can do a linear scan to give you basically you have an array that's an accumulated array of values. It's sort of a dynamic programming approach. Accumulated array of values that gives you at any particular index the sum from the beginning index to that index inclusive. You basically populate that array. And then what you can do is you can take the difference between two different indices in that array to give you the sum. I think you have to take the two different difference between the indices and then add probably the value at the initial index, and that'll give you the sum, the inclusive subarray sum in constant time. That's the key. So you can do that in constant time given those two indices after you do this pre-processing step. So it's linear pre-processing step and then constant time to figure out what each of those sums would be. And you would make that a subroutine. Now what you do is at each index A from left to right, you say, okay, I want to do a binary search to find the minimal index such that the sum, the subarray sum, which you could find in constant time from that starting point, where that the minimal index, the furthest to the left index I could find, where it's this condition is met, where the total is greater than or equal to S. And you can do a binary search from there. So you'd start at the middle, and then you say, okay, if I'm larger, then we want to go to the left. If I'm smaller, then we want to go to the right. Right, and then you can check the size in constant time. And then you stop when so if you're larger, so actually, yeah, if you are, if just thinking, once you're on the edge, you're larger, you want to go to the left to be smaller. And if you do that and you're now too small, you would want to go to the right. You might still be too small, you go to the right again, you're still too small. You keep going. When do you stop? I think you can. The tricky thing about that is you don't want to have to code it properly so that the search, so that way you don't end up basically, I guess, missing the index. Yeah, no, that's fine. I mean, you can do a, you can just take like take the min of each index that works, take the minimum of it, right, and save it, and then right, you just go left if you're greater than or equal to, you go to the left. If you're less than, you go to the right. And at some point, you're going to end up finding. No, I'm sorry. That's a weird. That's an awkward kind of a binary search, isn't it? Because you want greater than or equal to, and you might end up jump to the left, and then you're smaller, and you go to the middle, and you're still smaller, and you go to the right again, you're still smaller. I guess you don't want to throw out the endpoints, sort of like that's the thing with the binary search, is that you kind of do want to throw out endpoints if you can. However, in this instance, I guess what you would want to do is you don't want to throw out endpoints, and you just throw, and you finish, you stop when you are at the when they start and the endpoint are equal to each other, the left and the right, sort of where you're sort of in the range. When the range is size 1, that's when you stop, and you don't throw out the endpoints. And now the tricky thing here, though, is if you go all the way to the end, the right side, you kind of want to check that first to see if the right side, if you start start point is all at the right side. You want to check that, because if it's not less than the total, then you scrap the whole thing. You would go to the right. There's nothing to go to the right to, so you just end there and terminate early. There's no solution you'll find. Interesting. Yeah, it would be inclusive in A and inclusive of the end of the range. And you would, first check you want to do is to see if that is less than or equal to S, or greater than or equal to S. If it is, then you can continue. If not, then you want to terminate early. Yeah, it's kind of a funky binary search on that one. Definitely one of the funkier ones. Just thinking if you can employ, C++ has a like a binary search that's built in. I'm wondering if you can employ that, the built-in. It's like I forget how it goes. It's like upper bound, lower bound. Yeah, that's what you're looking for. So I want to say you can employ like the upper bound or the lower bound. However, the problem with that is that you would have to use a lambda, I think. I think you can. I think you could just use the upper bound or the lower bound. It would work too. All elements which the expression is true must precede all elements which the expression is false. Pointing to the first element of the range that is greater than the value, or no such element is found. Now the problem with this, yeah, just thinking, it's a little funky because we're working with indices. Although you can convert the pointer position to, like, you'd have to use a comparator, and you can actually use the pointer position to get the index, and then you can use the indices to generate the sum. Yeah, and you want what is it? You want this sum. Yeah, look at the sum. It's going to be the first element in the range from left to right that is greater than the value S. You actually want greater than or equal to, so you don't want the lower, but it's not less than, so greater than or equal to. Yeah, that's really interesting. So actually this algorithm should work in theory. Huh. Super interesting. Excuse me. Yeah, you could use this lower bound though, so do what we want. Kind of tricky, but it works. Yeah, implementing this lower bound is really what. Maybe I should write my binary search routines like this, because that kind of handles what I was describing about. Are you practicing for a job? Also, good job. Thank you. Hey, welcome back, Fedo. Hello, hello. Welcome again. Sort of. Yeah, I'll explain in a minute what I'm practicing for. Thank you. I should probably write my own. I should probably use these the upper bound, lower bound templates for. This is, wait a second. This is not less than and greater than. You can also reverse. You could reverse the comparators. That way, basically it uses the list in reverse, and then you'd end up getting the not greater than. You would get the less than or equal to. You could do the same thing. So the difference between these two, I think, is only. Not less than, yeah. This is iterator less than value, and then you just do not. You just do a flip and a negation in there, or really it would be less than, and then if you put this is greater than or equal to, so really you just put an equal sign in here. This would be the same thing. The reason why they use the negate this not with the things flipped is because you can use a custom comparator, and so it to value compared and then not value to it, so that allows you to do the this allows you to get the greater than or equal to versus just greater than. But what I should do, I should actually write all of my, I should really write all of my my booleans, my binary searches when I write them like this template with a comparator in there, the negation comparator, and then the, right? And the reason is because this gives me a lot of consistency. In other words, I don't have to think of like how I'm going to write my binary search every time I'm going to write it, because I've run into that problem many times where I'm like, okay, I know I need to write a binary search, but I get hung up on, as you just heard me describing it, like how am I supposed to write my binary search? Excuse me, so it works on that data set, so it doesn't cause problems and to fail. And really, I should just be like copy pasting this, basically, just have this memorized, and you just modify it slightly if it's a less than or equal to, or just there's a greater than or greater than or equal to, is just that's the difference between these two. And then if you need basically to do the other side, which is like effectively have the elements reversed more or less, if you want to do instead of there's greater than or equal to, but you want to do less than or equal to, then your comparator just needs to be the other direction, right? You just modify your comparator, so that way instead of it being true on the left side and false on the right side, it flips to false on the left side, true on the right side. Basically reverse sort your condition, and then it would work in the other direction, or not in the other direction, but it would be from left to right. The first element that's yeah, right. If this is greater than or greater than or equal to, then it would be first element that's less than, and the first element that's less than or equal to. Yeah. So and that should be sufficient basically for pretty much all the binary search needs, I think. I believe. Yeah, I get kind of hung up sometimes with my binary searches, but I'm pretty sure you can modify. You can just use the upper bound, lower bound implementations pretty much in all cases, I want to say. But yeah, so that's what you would do. That's it. To do the n-log-n problem, that's basically it. Is that at each index you do a binary search for the other index, and you do one linear pass pre-processing step. So that way, all of the comparisons can be done in constant time to figure out what the subarray sum would be. Yeah, that's how you do n-log-n. That was really long-winded explanation, but that's how you would do that. So this is a good question. This is a good one. I like this one. It's a pretty straightforward question. Kind of can and should be done quickly, but I mean, it took a while. I don't know. I mean, I had to kind of think about it, I need practice, and I also had to really think about how I would do the n-log-n solution. I don't know, man. I guess I'll get faster at this too as I go, you know? I'll get faster. But, yeah, let me explain why I'm doing all this before we explain why I'm doing all this before I go to, before I get going. Let's just see if I missed any. I did. I have one here. And then another one. Oh no. Okay. Only done a couple hundred problems. Most of the medium problems, most of the problems I've done here have been the easy ones. I have a lot more to do, a lot to go. I've only not even done a third yet. Well, they keep adding questions. The beginning of the year I had about a third. But yeah, I've got a lot to do, a lot of work to do with these. Why am I doing this? Let me answer that question. Yes, it's for job interviews. I work as a software developer. I interview relatively frequently for software developer positions, and I've struggled with these interview questions in the past. I mean, I've done thousands by now, over 1,000 by now of these on the internet, over different websites. So I'm pretty well versed in this stuff, I'd say at this point. Like obviously on this particular website, I've only done a few hundred, but across a few different websites, I've done a few hundred. Pretty confident I'm over 1,000. I'm like a few hundred problems over 1,000, I think by now, different programming questions. But could always use more practice. And yeah, I want to finish all the problems on this site. And I think once I've done that, then I'm probably in good shape for all of the interviews after that in terms of just the coding question, like the algorithm questions. There's a lot more to programming than just the algorithms though. So yeah, it's, I've got a lot of work to do, I guess, beyond that too. But yeah, basically just interview practice. That's all. Just keep my skills sharp. Best of luck. Thank you. Yeah, I mean, I have a job already. Like I don't actually necessarily need or want to get a new job. I've been looking and trying to find a new job, but actually I'm in a position now where I don't necessarily need to. But yeah, thanks. Yeah, I'm gonna cut the video here too. It's just kind of a long video. But thank you, and thank you all for watching, hanging out, saying hello. I do appreciate it. I'll talk to you all soon. And yeah, I appreciate it. That was, what problem was that? That was the minimum subarray sum, minimum size subarray sum question. That was a good one. I like that one. All right, take care. Talk to you soon.